Modern 3D sensors map the physical world by firing millions of laser pulses, instantly returning a highly detailed point cloud environment. For AI to understand raw physical space, it must learn to interpret this data. Standard convolutional neural networks, or CNNs, cannot natively process this information. They require perfectly ordered grids to function, much like the rigid arrangement of pixels in a standard 2D image. To force 3D data into these networks, engineers converted it into voxel grids, essentially creating 3D pixels. But a voxel grid bounding a chair consists mostly of empty space. You end up wasting massive amounts of computational power processing the empty air around the object. A point cloud sidesteps this volumetric waste. It is simply a raw mathematical set of points, with each individual point defined by an x, y, and z coordinate. This schematic demonstrates PointNet, the pioneering neural network architecture built to process point clouds directly. As shown, it acts as a unified framework capable of classifying entire objects, segmenting specific structural parts, or parsing the semantic layout of a room. Bypassing the voxel grid eliminates computational waste, but stripping away the rigid grid removes the sequence neural networks rely on. The architecture is left with the burden of interpreting data where the order of points is entirely arbitrary. A raw point cloud is an n by 3 matrix. N is total points. 3 is the spatial coordinates, x, y, z. Standard networks process this sequentially, row by row. But if shuffled, the 3D shape remains exactly the same. The cloud has no inherent order. A point cloud containing thousands of points has an astronomical number of possible matrix arrangements, specifically n factorial combinations. Processing this effectively requires a property called permutation invariance. This imposes a strict engineering constraint. No matter which permutation is fed into the network, the final mathematical output must remain absolutely identical. Achieving permutation invariance required engineers to discard traditional sequential network designs. They needed to discover a mathematical operation capable of treating the data for what it truly is, an unordered set. How do you build a network that purposefully ignores the order of the information it receives? The first logical attempt was to simply sort the points into a predefined order before feeding them into the network. Sorting fails in high-dimensional space. There is no mathematically stable way to order points across multiple dimensions without destroying their exact spatial relationships. The next attempt used recurrent neural networks, or RNNs, treating the list of points as a sequence in time. RNNs process short sequences effectively, but they cannot scale to track thousands of unordered points. The geometric signal degrades long before the network processes the entire object. The solution required a specific mathematical concept, the symmetric function. A symmetric function is any mathematical operation where changing the order of the inputs produces the exact same output. Simple addition and multiplication are basic examples. If engineers could anchor an entire neural network with a symmetric function, it would act as a universal continuous set function approximator, rendering it completely immune to the n factorial problem. PointNet executes this strategy by mapping the individual points into a much higher dimensional space first, and then applying the symmetric function to aggregate them. The process begins by feeding the n by 3 matrix into a multi-layer perceptron, or MLP. An MLP is a standard neural network layer, but here it is structured to process every single row of the matrix completely independently. The crucial engineering detail is that the weights within this MLP are perfectly shared across all n points. Every point is subjected to the exact same mathematical transformation. As a single point passes through the network, its 3 spatial coordinates expand into a 64-dimensional feature vector, and finally into a 1024-dimensional feature vector. The network is lifting the point out of standard physical space. It translates raw coordinates into a high-dimensional vocabulary, capable of encoding complex spatial patterns. Because the points are processed in total isolation by the exact same shared weights, their original order in the matrix still has zero effect on their individual transformations. This shared MLP architecture prepares the data for aggregation while preserving the strict independence required by set-based mathematics. We now have an n by 1024 matrix. The network holds 1,024 distinct high-dimensional features for every single point in the cloud. To aggregate this massive matrix, PointNet applies its symmetric function, global max pooling. Max pooling slices vertically through the n dimension, evaluating one feature column at a time across all the points. For feature dimension number 1, the network scans all n points and extracts only the single maximum activation value. It repeats this process across all 1,024 dimensions. The massive n by 1,024 matrix collapses entirely into a single 1 by 1,024 vector. This final 1 by 1,024 vector is the global shape descriptor. It represents the network's complete understanding of the 3D object. Because the max pooling operation is indifferent to the order of its inputs, this global signature is strictly permutation invariant. The architecture has successfully moved beyond sequence-based processing to handle the native, unordered mathematics of 3D point sets. What physical meaning does this abstract 1 by 1,024 global feature vector actually hold? We can trace the max pooling operation backward to identify the specific input points that generated the maximum values. This extracted group is called the critical point set. Out of thousands of input points, only the points that won the max pooling operation contribute to the final shape descriptor. This surviving subset of points visually forms a sparse geometric skeleton of the original object. The network learns an optimization function that evaluates the cloud and selects only the most informative structural anchor points. PointNet does not memorize the dense surface of a 3D object. It abstracts the absolute minimum structural framework required to define its geometry. The critical point set provides a highly practical engineering consequence: extreme robustness to data loss. This diagram shows the effect of deleting non-critical points from the original input scan. Even when paring the object down to its bare skeleton, the global feature vector remains at 100% stability. Because the deleted points did not trigger the maximum activations in the first place, their absence mathematically cannot change the final output vector. The inverse concept is the upper bound shape. This mechanism dictates how PointNet handles the injection of noise or outlier points. You can add random noise points up to the boundary of the upper bound shape. As long as these new points do not trigger higher internal activations than the critical skeleton, the network ignores them entirely. By respecting the unordered mathematics of point sets, PointNet established a 3D deep learning framework fundamentally resilient to the chaotic reality of physical sensors.